Hello, my name is Jorge Zerpa, and I will present an application of set propagation and finite element methods to transient problems in solid mechanics. This work was developed with Marcelo Forex and Daniel Freire Caporale, working at Universidad de la República in Uruguay, with the financial support of Comisión Sectorial de Investigación Científica and Agencia Nacional de Investigación y Innovación. I will start with a brief introduction to the problem and present some preliminary concepts. Then I will describe the method developed, present the numerical results, and enumerate the conclusions. Transient problems are those with state variables that change in time. In solid mechanics, we can find several of these problems, such as heat transfer and wave propagation. The resolution is required in different relevant applications, such as wind energy production, design of massive structures, or even simulating the effects of COVID-19. The numerical resolution of these problems is a challenging task, and new methods keep being developed. Moreover, real-world problems include uncertainty in parameters and input sources, and the common approach is to simulate and test, which becomes computationally intractable in verification problems. Our goal is to develop new resolution methods for input sources with uncertainties. Our approach is to combine two methods. On the one hand, the gold standard method for PDE domain discretization, and on the other hand, an innovative approach for ODE's resolution. Let me present the idea behind the finite element method. To do so, I will consider this simple problem given by a solid with a stiff circular inclusion with two fixed points and a known applied pressure P variable in time. The continuum dynamics problem consists in finding for each time t the displacement field U solution of the partial differential equation 1. The finite element method divides the domain into elements and considers the balance equations for the discretized domain. The problem is then converted to this, where the continuum domain was discretized into a mesh of triangular elements with 600 nodes using the GMSH measure in this case. The displacement inside each element is interpolated using the nodal displacement values. The partial differential equation is now a system of 1.2 thousand ordinary differential equations, and the vector capital U contains the displacements x and y of the nodes of the mesh. The differential equations for general linear heat transfer or structural dynamics problems have these expressions, and both have standard numerical integration methods commonly used. The most relevant methods are shown here, in which the time domain is discretized and the balance equations are imposed at certain time steps. These methods are implemented in a library called ONSAS, which is an under development open source tool for nonlinear structural analysis. It can import GMSH mesh files and write BTK files. At onsas.org, you can browse the current version of the documentation and the code. This is the tool that will be used in this work. In this particular example, we can use ONSAS to solve the problem and obtain this plot of the magnitudes of the displacements. The load applied is an impact pressure, and we can observe that since the inclusion is stiffer, the wave propagates at a higher speed on the left region as expected. Now, let us introduce the ideas behind set propagation methods. As we said, when uncertainty is present in the input sources, the simulation approach becomes intractable. A prominent framework used to solve verification problems consists in using unions of sets to cover all the exact solution of a dynamical systems for all the initial states and all admissible inputs and parameters. Such approach is called reachability analysis. The methodology we are proposing might enable the development of new applications in engineering problems. This approach is implemented in tools such as JuliaBridge, a library focused in the development of efficient methods for reachability analysis and related computational problems. It is implemented in Julia and is also hosted in GitHub with extensive documentation available. This is the tool used in this work for reachability analysis. Now I will describe the methodology developed. The method consists in 3 steps. First, the differential equation system is converted into an homogeneous and first-order form. Then a set omega 0 containing the trajectories of all the exact solutions between 0 and delta is constructed. And finally, that set is propagated for the following times using the state transition matrix. To present the steps of the method, I will use a simple example, a single degree of freedom problem, which can describe a spring mass system. 2 cases for initial conditions are considered, a single condition and a hyperrectangle set. For the spring mass problem, the first step of the method consists in the order reduction. Then, defining the variable x, we obtain an equivalent formulation as a system of 2 differential equations of first order. For the second step, in the single initial condition case, we show here the phase space. The green circle is the initial condition, the yellow circle is the analytical solution at time delta, and the set omega 0, as we can see, includes the analytical solution. For the case of a set of initial conditions, we can see that the analytic solutions are included in the set omega 0 as well. In the last step of the method, the set omega 0 is propagated for each following time interval, and the obtained sets can be represented using different set representation strategies with different levels of accuracy and computational costs. In the case of a set of initial conditions, the propagated sets also include all the trajectories of the exact solutions of the system. Here we can see a plot of the displacement and in time for the first seconds. Here are the displacements after 2 periods of time of simulation, and we can see that the set-based method provides more accurate solutions than the standard numerical methods. Let us now see the numerical results obtained. To show the results regarding the accuracy of the method, we consider a unidimensional wave propagation problem from the cited reference. The domain consists of a bar clamped on the left and submitted to a step force on the right. The problem is governed by the partial differential equation 8. The continuum domain problem has an analytic solution shown in equation 9. The domain is discretized using 1000 elements, and we obtain this reduced stiffness and mass matrices. No damping matrix is considered in this case. The nodes are numbered from left to right. The displacements obtained for node 700 are shown here, and we can see the peaks, which show the time when the wave is passing through the node. Here we can see a zoom of the plot where the flow pipe with the set solutions is more accurate than the numerical integration methods. Here we see the velocity at node 700. And once again, we see the zoom showing the higher accuracy of the set-based method. In the following problem, we solve a realistic model for concrete casting heat of hydration. The problem is motivated by the design process of massive concrete structures. Maximum temperatures during curing must be safely estimated in order to avoid cracks developed in the structure. Given the symmetry of this problem, a quarter of the domain is meshed and analyzed using ONSAS. These are the parameters considered. And the external temperature is assumed to have a sinusoidal variation, and the heat of hydration is modeling using an exponential law. Using a fixed parameters set, we obtain these plots for the temperature distribution and these temperature evolutions for the control points. We can see that numerical methods provide slightly lower values of temperature around 51 hours. As expected, the temperature closer to the center of the massive piece of concrete is higher than the control point closer to the frontier of the domain. Considering variations in the level of heat and the external temperature, we obtain these plots, which provide a key result for safe design and verification of these kind of structures. We can conclude that this combination of methods is a promising tool in engineering verification problems. The method provides accurate solutions compared to reference numerical methods, and the method allows to obtain solutions for distributed initial conditions. Several work lines are opened, including parameter uncertainty, extensions to nonlinear analysis, and considering probability distributions in the initial states. These are the references cited. And thank you for your attention.